Hello and welcome to this presentation of the RAM configuration controller, which configures the features of the internal SRAMs, SRAM1, SRAM2, SRAM3, and backup SRAM. The RAM configuration controller is in charge of handling the error code correction, or ECC, disabling ECC through a software sequence based on a key register, performing global SRAM erasure through a software sequence also based on a key register, protecting SRAM2 against write accesses for each 1 kilobyte chunk. The STM32H5 03 microcontroller differs from STM32H56X and STM32H573 regarding the SRAM features. STM32H503 supports ECC on SRAM1, SRAM2, and backup SRAM. STM32H56X and STM32H573 support ECC on SRAM2, SRAM3, and backup SRAM. SRAM3 is present only in STM32H56X and STM32H573. This table summarizes the features of the internal SRAMs. Let us start with the features supported by all internal SRAMs. Automatic erasure when product state regression is performed, capability of software-initiated erasure. All SRAMs except the backup SRAM can be erased on a system reset. The contents of backup SRAM is retained in standby and VBAT modes. SRAM2 and optionally backup SRAM are protected by the tamper detection circuit and are erased by hardware in case of tamper detection. The ECC is supported by SRAM1, SRAM2, SRAM3 and backup SRAM depending on the exact reference of the microcontroller when enabled with the related option bits. The SRAM2 is made of 64 1 kilobyte pages. Each 1 kilobyte page can be write protected by setting its corresponding PXWP bit in configuration registers. This slide describes the SRAM1, SRAM2 with ECC and SRAM3 with ECC memory map for STM32H56X and STM32H573 devices. 4 64 kilobyte blocks of SRAM3 and the 64 kilobytes of SRAM2 are ECC protected. Regarding SRAM3, the ECC codes are stored in a dedicated part of the SRAM, the upper 64 kilobyte part of SRAM3. This area shall not be used by applications. Regarding SRAM2, the information which is stored in 39-bit wide 32-bit data plus 7-bit ECC. Consequently, the entire SRAM2 is ECC protected. ECC error detection is reported to the Cortex-M33 as follows. Single error detection and correction cause a maskable interrupt request. Double error detection causes a non-maskable interrupt or a maskable interrupt. The failing address is latched in a register. This slide describes the SRAM1 and SRAM2, both with ECC memory map for STM32H5 devices. The 16 kilobyte SRAM1 and 16 kilobyte SRAM2 are ECC protected through 7 ECC bits added per 32 bits of SRAM. The error report mechanism is the same as the one implemented in STM32H56X and STM32H743. ECC can be automatically enabled by programming user option bits in the flash memory. ECC can be disabled by executing a software sequence that writes keys into ECC key registers. Since ECC requires a read-modify-write operation when writing partial data, byte or half-word, the performance can be measured with and without ECC. When ECC is disabled in SRAM3, the last 64 kilobyte block containing the ECC codes is accessible by masters. This can be used for error injection. When ECC is enabled in SRAM3, this area is reserved and cannot be accessed by masters. The SRAM2 is made of 64 1 kilobyte pages. Each 1 kilobyte page can be write protected by setting its corresponding PXWP bit in the RAM-CFG Memory-2 write protection 1 and 2 registers. 2 registers are necessary to form a bitmap of 64 bits. The consequence of attempting to write protected page is that the SRAM controller returns an error response to the AHB master. When this master is the Cortex M33 CPU, this error causes a bus fault exception. When this master is a DMA channel, this error is interpreted as a DMA transfer error. SRAM arrays can be requested by executing a software sequence based on keys that have to be written to key registers. SRAM busy flag is set in the related SRAM interrupt status register as long as the erase is ongoing. The total duration of each SRAM erase is equal to n AHB clock cycles, where n is the size of the SRAM in 32-bit word units. If the SRAM is read or written while an erase is ongoing, wait states are inserted on the AHB bus until the end of the erase operation. SRAM arrays can be requested by executing a software sequence. 1. Write 0xCA in the RamCFG SRAM-X erase key register. 2. Write 0x53 in the RamCFG SRAM-X erase key register. 3. Write 1 in the SRAM-ER bit of the RamCFG SRAM-X control register. The RAM configuration controller generates the following interrupt requests: a regular interrupt in the event of a single error detection and correction, the non-maskable interrupt or maskable interrupt in the event of a double error detection. Status registers provide the current status of these events, the address at which a correctable error has been detected, and the address at which a non-correctable error has been detected. Note that these addresses are locked until software clears the address latch enable bit in the control register. The table indicates the effect of low power modes on the RAM configuration controller. Sleep mode has no effect. RamCFG interrupts cause the microcontroller to exit the sleep mode. In stop mode, the contents of RamCFG registers and SRAM contents are kept. However, ECC error interrupt, or NMI, doesn't cause the microcontroller to exit the stop mode. In standby mode, the RamCFG module is powered down and must be reinitialized after exiting standby. Thank you for attending this presentation on the RAM configuration controller. In addition to this presentation, you can refer to the presentation on power management.